Hi and Assalamualaikum. My name is Shafa Ashraf MC and I will tell of you about the background of this study. This study are focusing on the production and purification of nitric oxide for medical application, particularly in managing pulmonary hypertension and neonatal oxygenation. And we will highlight the need for high purity nitric oxide to meet stringent medical standards amidst in rising global demand. For the production analysis, we have investigated catalytic oxidation of ammonia with excess oxygen. To establish this optimal condition, we have prepared the temperature around 800 to 950 degrees Celsius in controlled pressure setting, and we utilize a catalyst using platinum radium catalyst to enhance the reaction rate and selectivity. For the achieved production capacity, we have achieved around 3,600 metric ton of nitric oxide per year with high conversion efficiency. For the purification process, it uh, it is essential for removing trace impurities such as nitrogen dioxide, residual ammonia, and sulfur dioxide. We have implemented an absorption-based purification system using activated carbon, and we have designed a fixed bed absorption column with a temperature swing absorption (TSA) for the process for regeneration, ensuring continuous efficiency and absorbent integrity. For the next part, which is introduction of the subjects, in the reaction engineering part, we will explore about the production of nitric oxide, and we will examine the catalytic oxidation of ammonia, the kinetic of the reaction, the catalytic system and reaction condition, and we will explore the design of the suitable reactor system. And for the separation process part, this presentation will explore about the purification system, purification of nitric oxide to make the high purity of nitric oxide. And in this presentation, we will examine the impurities of in the production and the selection of absorption-based purification system.
Hi, my name is Eldridge, and I'll be explaining the process flow diagram which was used in our IDP and was generated using symmetry simulation software. As you can see from the diagram, it starts with ammonia and oxygen, enters separately at 25 degrees Celsius and 100 kPa, then mixed in a mixer M1. The mixture is then compressed to 500 kPa in compressor 1 and preheated to 800 degrees Celsius in heater 1. The mixture is then enters plug flow reactor where the ammonia will react with oxygen to form nitric oxide NO and water vapor. The chemical equation for the reaction is 4NH3 plus 5O2 to produce 4NO and 6H2O. There will also be a small amount of NO2 forms due to excess oxygen. The side reaction chemical equation is 2NO plus O2 to produce 2NO2. The outcome is optimized NO production, which is essential for nitric acid manufacturing. Thank you.
So for the kinetic of ammonia oxidation, the primary reaction for the ammonia oxidation is 4NH3 plus 5O2 will convert to 4NO plus CH2O with the delta H of negative 1170 kJ per mole in the high temperature and with the help of catalyst of the platinum base in high temperature of 800 to 950 degrees Celsius and 1 to 10 atm to achieve over 90% of conversion efficiency. And for the side reaction for the ammonia oxidation, we will have a formation of nitrogen, N2, and nitrous oxide. And these are the unwanted product, and the unwanted product can be controlled by optimizing the temperature and pressure control.
Hi, my name is Muhammad Zafran and now I will presenting about optimal catalytic system. The catalyst we use in our reaction is platinum rhodium due to high activity, high selectivity and thermal resistance. For high activity, the platinum rhodium alloy, 90% of platinum and 10% of rhodium offers high catalytic activity and selectivity toward nitrogen oxide. Next, highly selectivity. It reduces the side reaction and improving the overall process efficiency. Next, the thermal resistance. So, the reaction can begin in high temperature condition. Okay, next, optimal reaction condition for nitrogen oxide production. The first one is optimal temperature. The optimal temperature is in the range of 700 to 800 degrees Celsius. Next, pressure. For pressure, we need to use high pressure, that is 10 atm, leading to high NH3 ammonia conversion. Next, oxygen to ammonia ratio, that is the ratio is 1.2 to 1. The last one is residence time between 0.26 millisecond to 0.262 millisecond. That's next, production capacity of the system. For initial ammonia flow rate, molar flow rate, that is 14 kmol per hour. And the conversion, that is the final conversion based on simulation result, is 99.93%. The final nitrogen oxide flow rate is 13.92 kmol per hour. And the estimated annual production capacity is 3,654 ton per year. Okay, for the reactor type selection, we use in our reaction is PFR, that is plug flow reactor. The first reason is due to higher conversion. PFR allow a high degree of conversion per unit volume compared to other reactors such as CSTR and PBR. Next, the reason is PFR can reduce back mixing, so it can provide a uniform residence time distribution. The last one is because of heat management. This is essential because of this reaction is exothermic reaction.
Hi, I'm Auyumin Halina and I'll be presenting the separation process part. Identification of impurities. High purity of nitric oxide, NO, requires the removal of impurities that stem from raw materials, site reaction and environmental exposure. The most concerning contaminants, nitrogen dioxide, NO2, ammonia, NH3 and sulfur dioxide, SO2, pose risk to respiratory health and compromise NO stability. Moisture and trace metals further contribute to unwanted reactions, leading to corrosion and chemical instability. Without effective purification, these impurities undermine therapeutic efficiency of NO. A robust purification system is necessary to meet strict medical safety and quality standards. Selection of adsorbent. Activated carbon was chosen as the primary adsorbent for its exceptional ability to capture impurities. With a large surface area and a high porosity, it efficiently removes NO2, NH3 and SO2. Its strong affinity for polar gases ensures selective adsorbent while allowing NO to pass through. Additionally, activated carbon's chemical stability and recyclability make it a cost-effective solution, as it can be generated through thermal and pressure swing desorption. This combination of efficiency, reliability, and economic feasibility make it an ideal choice for NO purification. Adsorption isotherm. Understanding the interaction between NO2 and activated carbon is the key to optimizing the purification process. The Freundlich model was selected because activated carbon's heterogeneous surface supports multi-layer adsorption. Experimental data confirm its effectiveness, yielding key parameter K equal to 0.619 and 1/n is equal to 1.039, indicating strong adsorption. The log-log plot further validated the model, demonstrating that activated carbon effectively capture NO2. These findings reinforce the absorption system's reliability in achieving high purity of NO.
Hello, I'm Zorin. Now I would like to present about the design of the absorption column. For our specific application, we decided to choose fixed bed absorption column. This selection is based on the fact that the fluid we're treating will pass through the packed bed at steady flow rate. This allows for consistent and efficient contact between the fluid and absorbent materials. To prevent any unwanted reaction between the fluid and the column structure, we need a material that is corrosion resistant. In this case, stainless steel is an excellent choice, ensuring the integrity and longevity of our absorption system. Based on previous research, the suitable MTZ for activated carbon is approximately 0.8. However, in this case, we use an outlet flow rate of 13.89 kmol per hour, which is obtained from the reaction engineering part. We assume the molar volume to be 22.4 meter cube per second for ideal gas at STP, and we also assume the superficial velocity to be 0.3 meter per second based on information we obtain. Then from here we can get area and the column diameter, which is 0.2881 meter square and 0.606 meter. The figure above shows the breakthrough curve for NO production using an activated carbon adsorbent. Since the research provides relevant data, we have decided to estimate the breakthrough time based on this diagram. Next, assuming that the breakthrough time is 0.9 minutes, equivalent to 54 seconds, we can calculate the column height using the formula shown above. Based on research, the typical mass transfer zone MTZ range between 0.5 and 1.5. Therefore, we need to multiply the obtained column's height by the appropriate MTZ factor to determine the final column height. To further enhance our nitric oxide NO production process, we recommend focusing on optimizing the temperature swing adsorption TSA system within our purification stage. Specifically, we can improve NO production by maintaining high adsorption efficiency during the TSA process. This will directly lead to a higher purity of the NO delivered. Ensuring the TSA process prevents structural degradation of the adsorbent. A stable adsorbent translates to consistent and reliable NO output over time. Focusing on the cost effectiveness and scalability of the TSA regeneration, this will allow for future expansion and increase NO production capacity. Implementing NO chemical regeneration within the TSA system, this will help preserve the adsorbent integrity and ensure long-term stability of the NO production process. By implementing this recommendation, we can significantly improve the efficiency and output of our NO production.
So to conclude the presentation, in reaction engineering, we have explored about the catalytic oxidation of ammonia to produce a high purity of the nitric oxide. We have established an optimal reaction condition, which is around 800 to 950 degrees Celsius using control pressure of 1 to 10 atm. And we are using the platinum radium catalyst to achieve the production, which we target approximately 3,600 metric ton of nitric oxide per year with a high conversion efficiency of 99%. And for the separation process part, we also have developed an effective absorption-based purification system which utilizes activated carbon to remove trace of the impurities like NO2 and excess NH3 and SO2. We have also designed the fixed bed absorption column with a temperature swing absorption for efficient regeneration. And we have ensured a continuous operation and maintaining the absorbent integrity. Thank you.